Hey everyone, today I'm beginning a new series called Maths of Quantum Mechanics. Looking through YouTube, I found a lot of amazing videos giving an overview of quantum mechanics concepts. Things like the wave function, quantum superposition, and even quantum tunneling. But what I didn't find were very many videos giving intuition into the fundamental mathematics behind it all. I was surprised because I truly believe that the mathematics behind quantum mechanics can be made intuitive and understandable. So the point of this series is to take you from someone who knows quantum mechanics to someone who intuitively understands quantum mechanics and all the math behind it. And to give you an idea of what we will dive into in this series, here's a list of the chapters and the topics we will cover. These are all questions that I remember wanting intuition for when learning quantum mechanics, and hopefully you see questions that you have also always wondered. I plan to add more chapters as time allows, so if you don't see something that you've always wanted answered, please let me know. Now, before we begin, we need to go over the math I'll assume you're already familiar with. First, I'll assume you have a working knowledge of single variable calculus. In other words, you should be comfortable with derivatives, integrals, and Taylor series. You don't have to remember how to calculate all these, just have an understanding of what they are and what they mean. It's inevitable that we'll run into multivariable calculus, but we don't need it for the majority of the series. Second, I'll assume you're familiar with linear algebra at the level of 3 Blue 1 Brown's Essence of Linear Algebra. His series is fantastic, and it largely inspired this one, so I recommend you go watch it if you haven't already. It will be linked in the description. The linear algebra concepts you should be familiar with are shown on the screen now. Go ahead and pause it to look it over. Again, you don't need to remember how to calculate all these, just have an understanding of what they are. Hopefully this list isn't too daunting, and don't be afraid to brush up whenever you run into something unfamiliar. In this first episode, I want to show you all why we want to use linear algebra to model the quantum world. We're going to think like theoretical physicists and find that linear algebra pops out naturally by considering physical observations. First, let's review the basic mathematical model we have for classical physics. We know that a classical particle carries with it physical quantities, like position, momentum, and energy. As this particle moves in space and interacts with objects, we know that these quantities change continuously in time. So what are the takeaways? First, we know that classical physical quantities are single-valued, meaning they only take on one value at any one time. So, for example, a particle can't be in two places at once, and it can't have two different velocities. Second, physical quantities are continuous, meaning they vary smoothly as they evolve in time, and they don't change values suddenly. Given these two observations, it hopefully seems clear that the way to model these physical quantities is with a continuous function. A function, by definition, only takes on one value at any single time, and a continuous function doesn't have any sudden jumps. So, this is why in classical physics, we represent physical quantities with continuous functions. Now, this may seem kind of obvious. I mean, what else would we use? Well, to see when a model like this one breaks down, let us analyze a real physical system and compare the classical and quantum worlds. In particular, let's focus on a hydrogen atom, consisting of an electron in motion around a proton. Let's see what we expect to happen within the classical physics framework. As the electron orbits and falls towards the proton, it will release energy in the form of light. This is a well-known fact from electricity and magnetism. By measuring the energy of light released, we can have a measure of how much energy the electron has left, here in units of electron volts. So we can set up a detector and do exactly this. The electron's energy is shown on the left in units of electron volts, and, as required in classical physics, it is single-valued and continuous. Now let's hop into the quantum world and get an actual hydrogen atom and the detector, and let's see what really happens. we would find that we only get a few blips from our detector, measuring only a few energies. Okay, let's reset the experiment and give it another run. We only measure a few energies again, but this time some of them are different. We can repeat this experiment over and over again, and we would notice the following. First, it seems that we only get a certain set of energy values, never measuring anything in between. Second, the specific energy value that we measure is random. However, it does seem like some energy values have a higher probability than others. Let's summarize these conclusions and their implications. First, our experiment showed that physical quantities can sometimes be discrete, meaning we can list all the possible values it can take, never equaling something in between these values. Note that this contradicts the idea that physical quantities must be continuous. Second, the particular value that we measure is random but probabilistic. This means that before making a measurement, we do not know which of the possible energies we will get. However, we do know that some values are more likely than others, so there is a probability attached to each value. Note that this also contradicts the single valued characteristic, since before the measurement, we cannot determine a singular value for the quantity. It could be any of them. So clearly a continuous function won't work to model the quantum world. So what will? It may seem like a daunting problem to solve, but let's put on our theoretical physicist hats and see what we can deduce from our conclusions. First, let's find a way to mathematically model the randomness problem. It seems like before we make a measurement, the particle somehow holds the information on every possible outcome we could get. How do we mathematically represent this phenomenon? Well, let's say that we know for sure that the particle has energy A, and let us say that the particle is represented by the mathematical object m sub A. Now, m could be anything. It could be a function, an element of a ring, a manifold, just some mathematical object that we have yet to determine. Now, if the particle has energy B, then it is represented by mathematical object m sub B, and so on and so forth. So we have a mathematical object m for every possible outcome we could get for a particle. Somehow our particle is represented by an amalgamation of all these mathematical objects, holding on to each outcome until we make a measurement. So we need to put all these mathematical objects together somehow. Let's use some unknown dot operation. This dot operation could be addition, it could be multiplication, it could be something even more exotic. It's just some unknown way for us to combine our mathematical objects into one aggregate object that describes our particle before the measurement. This is a really good start. Next, we also need to somehow codify the idea that some outcomes are more likely than others. So each mathematical object also needs to carry with it the probability of getting that particular outcome. Well, the simplest way to do this is to just add a number in front of each mathematical object. A number that somehow encodes how likely each possibility is to occur. Now, let's take a step back and look at what we have. Having studied a number of mathematical structures in your past, hopefully you begin to see that this looks suspiciously like a linear combination of some sort. You see that, right? This is our only lead, so let's go ahead and run with it. Our particle is some sort of linear combination of all outcome possibilities, which we'll assume are represented by some sort of vector. This may seem like a big leap, but hopefully you see how we came to these conclusions. Now let's move on to the discreteness problem. This is now a question about how we represent our physical quantities. We know that functions won't work. We need a mathematical object that allows us to sometimes extract discrete values. This is a little more difficult, but if we follow our lead on linear combinations, we may guess that maybe linear operators, aka matrices, represent physical quantities. I mean, a matrix consists of a discrete set of numbers, so maybe we can somehow extract our physical quantities from that discrete set. So, putting it all together, we now have a really solid guess into how we want to model quantum mechanics. Particles are represented by a linear combination of vectors in some vector space, and physical quantities are represented by linear operators within that space. Now, if this seems somewhat contrived and unfamiliar, don't worry. We developed the framework of quantum mechanics in a handful of minutes, while it took the greatest physicists of the world years to arrive at these same conclusions. What matters is that you see why linear algebra is a good starting point for quantum mechanics. Now, there are still a lot of unanswered questions. How is a particle a vector? How are different probabilities calculated? How does a particle evolve in time? Next episode, we'll address the first of these questions and discuss what kets and wave functions are. Thank you all so much for watching.